I'd never heard about milking algae before. Our next speaker is Dr. Robert Duncan, Vice Chancellor for Research at the University of Missouri, Columbia. I know that many of the folks in this room saw the 60 Minutes show of last Sunday. It was very nice of them to show that cold fusion segment just before our energy summit. But it certainly is a fascinating story. And Dr. Duncan was featured in that 60 Minutes segment, having been recommended by the American Physical Society to serve as an independent scientist to look at the multiple claims of successful cold fusion experiments. Yesterday, Dan Cole from Ameren talked about the fact that there's no silver bullet to solving our energy challenges in the world. But I must say, he talked about the need for silver buckshots, and that's probably what we're going to need to do. But I must say, if this claim to successful cold fusion turns out to be real, and of course that's a big if, conceivably the world could have a virtually limitless supply of energy in the future. Let's hope. As an expert in low-temperature physics, Dr. Duncan has also worked for NASA, the Institute for Advanced Studies at Los Alamos National Laboratory, and the New Mexico Consortium, an organization that uses the strengths of New Mexico's research universities to build scientific connections around the world. He received his bachelor's degrees in physics from MIT, his doctorate in physics from the University of California at Santa Barbara. Please join me in welcoming Dr. Rob Duncan.
Thank you very much for that introduction. Hello. Well, thank you very much, and I'd like to thank the organizers for the opportunity to speak here today. Thank you all for coming. This has been a wonderful summit. I was really impressed by the focus and theme. We recently got our second Prius, so I don't know whether we have Priuses or Prii, but as a prominent representative told me here in Missouri, I don't emit smog, but I do emit smug, so I'll try to minimize my smug emissions with my Prius. But then to hear, T. Boone Pickens talk about the right way to go on energy policy, and with $2 billion, that's very enabling. So no one's going to stop him. So that's kind of interesting. And I'd say the most inspirational thing has been listening to the governor say that in these difficult times, it's time for innovation, it's time for discovery, it's time to lean into the challenges, not back away from them. I couldn't agree with that more. And so this has been a very, very exciting summit. What I'd like to do now is give you a talk that's more about the importance of objective scientific method when you approach new things you don't understand. It'll be more important to kind of take that away from this and how the media may play into or possibly hinder the ability to approach things that way, not to their fault, but to just the nature of mass media, than to really focus on the science. But let me say I would love in a different venue to go into extreme depth on the science. So hopefully we can schedule within the next month or so an opportunity to discuss the science in much more detail. All you really need to know before we get started is this cold fusion question, and we'll review it in just a second. You have an apparatus that has a tiny, tiny palladium foil, okay? This is only about 0.3 grams. So this foil is about 1/100th of an ounce. This foil is tiny, okay? And nonetheless, there have been reports by now, 20 independent laboratories all over the world that have reported exceptional heat releases on the order of what we call a million joules, which is pretty amazing. To put that in perspective, these spotlights are emitting about 300 joules per second each. So joules, a tiny amount of energy, but to get a million joules from a tiny piece of palladium foil, as has been reported, is really phenomenal. So try to set that scale. But all you really need to know here is that excess heat means you put in some amount of electrical energy into this foil to load it with a heavy hydrogen isotope called deuterium. And then you compare the amount of heat that comes off sometime later to the amount of electrical energy you put in. Okay? So I'm not going to go really into a lot of technical drawings or something like that. I'd love to do so in a different venue. But rather just know the excess heat is the amount of additional heat that comes off compared to the amount of electrical energy you put into the process. That's what we mean by excess heat. Well, with that, I'd like to go on and talk about the 60 Minutes piece. I actually had recommended the term cold confusion for reasons you'll see here in just a second. And it's interesting. Most people don't realize that the first report of a possible nuclear fusion reaction in palladium loaded with deuterium or heavy hydrogen occurred in Berlin, Germany in 1926 by two professors. And actually, when you go back and look at what they were doing experimentally, they were, in fact, seeing essentially the same physical system that we've been discussing at length today and since Pons and Fleischmann's press release in 1989. It's interesting that there's another type of cold fusion that is really, really well known and confirmed scientifically. In fact, this paper by J.D. Jackson that you see here from Princeton University at the time, Catalyst of Nuclear Reactions Between Hydrogen Isotopes by Mu Mesons. Notice it was published on Tax Day in 1957, if that was still Tax Day in 1957. But this is one of the best papers I've ever read. Very, very good. And I really, for those in science, I'd say this would be a very good thing to read. Now, this was fusion at near absolute zero temperature between hydrogen deuterium atoms that were in their liquid state near absolute zero. And again, this has been confirmed. The problem is mu mesons are rare, and after about 10 to 100 reactions, they stick to the alpha particle, or the helium that's produced in the nuclear reaction, and hence are taken away from the reaction. So that's what limits the ability for this to become a viable energy source. My first guess is there might be something here that applies to what we're being discussed now in terms of cold fusion, but I certainly don't know that for sure. I don't believe everything I think, and I ask you all to not believe everything I think. You know, the reason I'm an experimentalist is I can't believe everything I think. I have to conduct controlled experiments to figure out what's really going on. Okay? Well, now, when we go on, cold fusion continues, and this is an extremely important point, but now in the age of mass media, okay? Now in our modern media age. Well, in 1989, Pons and Fleischmann from the University of Utah held a press conference to announce that they had discovered this wonderful new form of energy that would alleviate all the world's energy problems, okay? That was, to say the least, a little bit of a jump, okay? They had seen some fascinating new science, science that now I realize after 20 years is real, okay? But the thing is that in seeing it, there was such excitement. You know, the idea of the University of Utah is, wahoo, okay, our ships come in. Press conference, announced to the world we'll solve the energy problem. Very, very bad media strategy, okay? Because after they were through their first lot of palladium metal, they tried to do it with a different lot of palladium metal, and they saw no results. Other researchers around the world tried to repeat Pons and Fleischmann's work. I heard that something like 60% of the sponsored research from the NSF, the project managers had requests to divert from the grant objectives to check this out, and it was generally awarded. So there was just a huge excitement to see if this was reproducible, and it was not, okay? And that created an extremely negative reaction by the physics community, especially in the United States, but I'd say all over the world, but especially a very negative reaction by the physics community. I would argue that it's understandable that there would be this angst by the physics community, especially after the University of Utah had made such a strong early case for this in their media strategy. But nonetheless, the point is that this negative reaction, I think, was worse than the initial concern of the media approach. What happened here is this very negative reaction resulted in what I consider to be a lack of objectivity. When I went on the 60 Minutes piece, I was contacted by a highly prominent professor from an Ivy League university who just really, really was angry with me for having done the piece. And the point was, I laid out the scientific case, but he flatly wouldn't consider it. And when I said, come on, why don't you just work with me here through the data, he said essentially, well, you know, us high-caliber physicists, you know, have done that before, and there's never been anything there. So you charlatans just can go on and do whatever you'd like. Okay, well, it's interesting. My scientific reputation, I guess, at least to him, had been stronger before I did the piece. But now, the point is, real science, possibly with outstanding engineering consequences, suddenly becomes a pariah science, a science where no one can go. Since that time, there have been hundreds of excess heat results from at least 20 independent laboratories that basically repeat the Pons and Fleischmann results. They don't all use the same apparatus, and I think that's important. They use about 5 different types of apparati, and those pieces of apparati all have different systematics. Nonetheless, they're showing excess heat. And that's interesting because with that scenario, the 60 Minutes story decided to engage. And I should just mention that my opinion of the negative media strategy, in fact, every opinion I express here today is strictly my own opinion, and it doesn't reflect the opinion of the institutions to which I belong, nor does it represent the opinion of any professional societies. But the 60 Minutes story, which aired on 4/1909, was reporting on a visit I made in October 2008 to Omar, Israel. And in Omar, they had observed excess heat while I was there at a fairly low level. There were 3 different cell designs, and all these cell designs, again, were very different at their location, and all have reported excess heat. Again, different systematics. The 5 cells that reported excess heat well before I was there were in fact a number that recorded excess heat, according to them. This was since 2004. 5 cells had reported excess heat exceeding 1 megajoule from a 0.3 gram or about 1/100 of an ounce palladium foil electrode. Now, the chemical heat release would have produced about 100 joule, maybe a few hundred joule of heat release if this were a stored, delayed chemical process. And I've had a lot of discussions with scientists here and elsewhere about that possibility. But the point is, the observed heat release in the extreme cases was on the order of a megajoule. I'd say much more typically, heat release from these cells that they see heat release, say, once a week or so, is on the order of maybe 50 kilojoules to 100 kilojoules. These megajoule or higher releases have only occurred 5 times since they've been doing this, I think, since 2003 or 2004. I'm not sure exactly when they started. There's another aspect, which is the heat out divided by the electrical energy in that goes into these systems. And that's equal to, in the case of their best result at 4 megajoules, 25. So you're getting 25 times as much energy out as you put in. You're getting lower quality heat energy out, and you've put in high energy electrical energy. 15, 8, and less are more typical. Now, quite similar results have been seen from many other labs around the world. Italy, EDNA, their national energy lab, Russia, China, Germany, and the United States, primarily Stanford Research Institute, or SRI, and not affiliated with the university, but SRI, to my knowledge, I'm not sure, and the U.S. Navy. And recently, particle tracks have been observed by the Navy SPAWAR unit in San Diego and reported at the March American Chemical Society meeting this year. And I understand there's work underway by the Naval Research Lab as well. Now, let me describe. You load, by one means or another, this heavy hydrogen into the palladium. You have to load to where you almost have 1 palladium atom per 1 deuteron, or heavy hydrogen atom. That sort of high loading is critical in order to see this effect at all. If it's below a loading factor of about 85% deuterium compared to the palladium concentration, then you do not see excess heat effects. And I think that's relevant. But again, I don't want to go into the ideas and technology and science today as much to continue on this course. But the point is that once this is loaded, it can take anywhere from a few tens of hours to a few hundreds of hours, it could be weeks later, before this excess heat effect starts to express. And that is very unusual. Also, I should mention that the conventional Pons and Fleischmann experiment showed excess heat about 1 time in 7 for that apparatus type that they used. They had other apparati that showed excess heat more like 70% of the time. But again, it hasn't been 100%. Navy SPAWAR tells me that their co-deposition technique of loading the palladium with deuterium shows excess heat 100% of the time. But they don't really carefully measure the excess heat in that experiment. They're looking for nuclear particle tracks. Well, so what's going on? We don't know, and it'll take a lot of well-controlled experiments to figure this out. There is no way to jump ahead. There is no way to take a random guess that's right. Scientific method is a wonderful thing. In my opinion, it's time to stop growling at each other from separate sides of this issue and employ the scientific method to figure out what's going on. The excess heat appears to be real to me now. First time I would ever say that, after having looked at the experiment very closely. For 20 years, I thought it was debunked. I thought it was junk science. Now it appears to be real to me for reasons that I can defend objectively. Now, my first hypothesis, now remember, I don't believe everything I think, so please don't you either. But my first hypothesis is, maybe back to 1957, there's a muon-catalyzed fusion of these deuterons that's near, but it's impossible that it would be directly in the palladium. The question is whether close proximity to the palladium would give rise to a larger, longer, sustained nuclear reaction than would be seen in free space. Possibly, again, hypothetically. Now, it's interesting because in this scenario, the muon-catalyzed fusion, again, has been one thing that was studied at the end of the 1950s and reported on so beautifully. So that's one possibility. It could be something completely different. We don't know until we apply a lot of careful experiments to figure it out. My message to the scientific community is, please, let's figure it out. One possibility is this nuclear effect, maybe muon-catalyzed, maybe catalyzed by something we've never seen before. But the possibility is that there is some evidence for this being potentially a nuclear effect. And this has been seen by microcraters found in these palladium electrodes once they're extracted from the experiment after the excess heat is recorded. And these experiments have been done by Energetic Technologies, where I was in Israel, and by the Navy Space War Laboratory. And obviously, I have permission from both laboratories to show you what I'm about to show you, because I think what I'm about to show you is pretty interesting. Sorry, it didn't come off very well. But again, this is just one possibility. I'm not saying this is what happens. I'm saying this is a starting place where I would start if I went into the laboratory to try to figure this out. One possibility is you could imagine something like a volcanic eruption, sudden release of energy, but at 100 million times smaller scale. And there's some evidence that that may be the case, but then again, it's not been studied systematically. Now, of course, the analogy is rough. I mean, this is geothermal energy. The hypothesis is that this could be a nuclear fusion energy release from D plus D in the palladium. Now, here's the evidence. These are scanning electron microscope images from Energetic Technologies in Israel, the lab I visited. Now, the interesting thing you see is that in the palladium surface, these are about 4 to 5 microns in total extent. There are these apparent regions of extremely hot ejecta, and there have been close studies to see whether the impurity concentration in the ejecta shows some type of thermal process, or whether instead it shows some type of chemical strafing effect on the surface that some unknown component inside the liquid might have created. Again, just don't know, but it is suggestive and kind of an interesting thing to observe. The people in Israel tell me, from their careful analysis, they're almost certain this was extreme heat release, slightly subsurface, and that the ejecta shows the isotopic migrations indicative of a very, very hot liquid ejecta that cooled. Now realize, this electrode was submersed in a lithium hydroxide, deuterated hydroxide solution, so it was bathed in a liquid. And in fact, in their extreme heat release measurements from 2004, they actually show where the electrode, this tiny little electrode, got so hot it boiled off the electrolyte. Okay? I didn't believe that at first. I said, okay, catching them off guard. I want to see corroborating evidence. Show me the thermal control of the thermal control system for the bath that surrounded this. Well, they dug it out. They showed it to me. The computer date stamped agreed with the date. And when I looked at that, this thing ejected or emitted so much heat, it threw the lauter, the refrigerated bath temperature control off, because the heat provided exceeded the cooling power of the refrigerator for the surrounding bath on the experiment. So, I was thinking maybe I can catch them flat-footed. I can't. It seems to me the science was well done. And a number of my colleagues will hate me for saying that. Now, when you look at this further too, these are just a few more that show the possibility of multiple clustered areas of extreme heat release in regions on the palladium surface. Now, the interesting thing is, in March 2009, at the American Chemical Society meeting, the U.S. Navy Space War Laboratory released this data. And they have a different growth technique. It's called co-deposition. So it's a different form of getting the deuteron into the palladium. But the point is, they see regions that appear to be regions of extremely hot ejecta. The Navy lab has gone further. They've thermally modeled what sort of subsurface heat release or surface heat release would be necessary to create this sort of ejecta. And they have concluded it must be of nuclear origin. But again, that's their conclusion that they mentioned in the American Chemical Society meeting last month. And it's suggestive, but if you remember, and for those of you who saw the 60-minute piece, they caught up with Dr. Fleischmann in England, and they asked him if he had any regrets. And he had 2 regrets. One, that he called it fusion. You can't jump there. You have to figure that out objectively. And 2, he regretted the news conference. And he claims he was kind of backed into doing the news conference. But again, those are his words, but not mine. Now, are there any lessons learned here? I sure think so. There is a huge gap between discovering a new scientific process and developing a useful engineered system. There are many, many, many things that can go wrong. This is way pre-Valley of Death stuff. Okay, pre-Valley of Death is there too. But there's also a lot of questions about figuring out what the phenomenology is. What is the underpinning basic fundamental science? We just don't know right now. I gave you my best hypothesis, first going in guess. It's just that, a guess. We need to stop speculating wildly. I mean, maybe imagine a piece, and by the way, I really appreciate the extreme professionalism and outstanding approach of 60 Minutes in doing the story. Scott Pelley, Denise Shetta, and Sam Hornblower were always very thorough and very courageous in their approach to the journalism. I really appreciate that. But what I mean to say is, imagine a piece that instead of talked about how you could have laptops that go forever and cars that only need a new energy source from time to time, imagine if instead they said, this is the process of scientific discovery. This is the process of how we figure out what's real from a new phenomenology we don't yet understand. Say we engage the public in understanding genuinely what the scientific method is. If we were to do that, I think we would be in a lot less trouble with our media interface than we often are. So often we say things that appear to be promises, and when the public doesn't see the laptops emerge that never need recharging, when they don't see, say, the automobiles that can go forever, when they don't see that materialize, then they hold it against the process of science. And I think we kind of set ourselves up for that by being over-speculative when we see something new and exciting we don't understand. Instead, engage the public in the process, the scientific method of how you make such a determination. Okay? Also, I think it's good to pursue basic science strictly because you don't understand. Who knows where it will lead? Who knows where an infant will be in society 40 years later? Nobody does. It's the same way. New science, you don't know where it's going to go, but that's no reason to stop having new science, right? So now, also, I really don't know if this science will ever lead to energy production, but I do know it never will unless we really go there systematically following the scientific method. Okay, mass media, I'm about to get hooked out of here. So mass media needs to approach new discoveries carefully because of that. Research funding always strives to be objective. People do extremely good jobs of that. And the scientific method is a wonderful thing. Use it always, no exceptions, even if it isn't politically correct, even if you're worried that you might get in trouble by your boss if you take a more systematic scientific approach, even if people go, oh, you're just an egghead, just jump ahead. You know the answer, don't you? No, you don't know the answer. Scientific method is a wonderful thing. Use it all the time. Well, thank you.
Ladies and gentlemen, we will now take a 10-minute break, followed by the technical tracks. Please remember to visit the posters on the second and third floor and the booths on this level.